Hey guys, how are you doing? Welcome back to another exciting video about YOLO object detectors family. We will go through YOLO version 2 in this video. Before going into YOLO version 2, we will recap about YOLO-V1. You can skip this if you already know the working of YOLO-V1. YOLO formulated object detection as a regression problem. That means all the losses are squared error losses. It is a single shot detector, which means all the boxes and class probabilities, everything it will do in a single pass. It learns better contextual features compared to region-based detectors. It uses the features from the whole image for the detection of objects. Now let's see the steps of YOLO-V1. So first thing is you resize your image into 448 by 448 and then divide your image into S by S grid cells. In the paper it is 7, so divide your image into 7 by 7 grid cells. Each cell can predict 2 boxes, but only one with the highest confidence score is kept. So finally, every square here predicts only one box. The grid cell in which the object center falls, that cell is responsible for predicting this particular object. Each cell predicts 2 bounding boxes and confidence score for each box. This confidence score is actually the objectness score. The total prediction vector is actually 7 by 7 into 30. So the first 5 values are for the first box, second 5 values are for the second box, and the last 20 values are for the class probability scores. Let's say if this image is passed through YOLO, we assume that these are the boxes we get for each objects here. For each of these boxes, 5 values are getting predicted. The first 2 values are actually XY coordinates. These are actually with respect to the grid center, distance with respect to the grid center. And then second 2 values are width and height. These are actually with respect to the total image width and image height. And the third one is objectness score. This only indicates whether this particular grid cell has an object or not. Whatever the box we are coming it here, whether it consists of an object or not. It is not giving any class information as of now. And the next 20 values are actually class probability scores. So 20 values because the Pascal VOC dataset has 20 classes. And the final confidence score for each box here is actually calculated by you take the maximum of all these probabilities and that is your final class for this one. And then you multiply this with the confidence score, which is objectness score. Once you multiply these two, you will get the final value. Like this, you calculate for every box here. So if there are 2 boxes for this one, for Apple, so for both the boxes, I will calculate these confidence scores. And then I will keep only the box with the highest confidence score. So if you see this particular box has the highest confidence score and the category which has the highest confidence score is Apple and cup and notebook. This is the network architecture. It has 24 layers, which means 24 convolution layers. And then 2 fully connected layers. And this is the training process. You pass the image, you calculate the labels here, and then you pass the image through the network, you get the predictions. From this you calculate the loss and then you backpropagate to update the network. So it is trained on Pascal VOC dataset which is having 20 classes. And this is the loss function. This green component is actually loss for the grid cells which are having an object, and this is for the grid cells which are not having an object. That's all. This is the quick recap about YOLO-V1. You can go through my previous video for a deeper understanding of YOLO-V1. Now let's come back to YOLO version 2. The aim of YOLO-V2 is to make V1 better. YOLO-V1 was actually faster than faster RCNN, but it is less accurate. If you observe here, there is almost 10 MEP difference. Also, it did not predict the object locations and sizes properly. If you look at this car prediction, this particular box is offset here. At the same time, bicycle has 2 boxes, different offsets. Even this truck has a bit offset from the actual original ground truth. The boxes are not properly fitting the object here. 2-stage networks seem to work better than the single-stage detectors for localization, especially faster RCNN. The localizations are much better compared to YOLO. However, SSD, another single-stage detector, broke the record by being more accurate and faster than YOLO. So it is more accurate than even faster RCNN and it is even faster than YOLO. Then our authors Joseph Redmond and Ali improved their YOLO version 1 and they have released YOLO version 2. YOLO version 2 is better than SSD and faster RCNN. They made series of changes on YOLO version 1 to make it better. So these are some of the changes they have made on the YOLO version 1 architecture to make it better. You can see that the accuracy has improved from 63 to 78%, which is huge jump. Also, they have introduced a new backbone network for the classification, which is very lightweight, having very good FPS. At the same time, it has good top 1 and top 5 accuracy scores. They also wanted their object detector to recognize a wide variety of objects. As you know, the Pascal VOC has only 20 classes. But what if I want to detect hundreds of classes? How do we design the setup for training an object detector for thousands of classes. So that's what they call it as YOLO9000. To be specific, they have detected 9000 classes in this one. We will discuss more about this in the next video. In this video, we will concentrate on YOLO-V2 for Pascal VOC and Coco datasets. Let us start with modifications they made to YOLO-V1 network first. So they have applied batch normalization to all the convolution layers. In YOLO-V1, there is no batch normalization layer. We all know that batch normalization actually stabilizes the training process. So the model converges easily, much more easily with batch normalization. It also has the regularization effect. So it avoids the overfitting problem. So what they have done is, they have added the batch normalization to all the convolution layers in the original YOLO-V1. So this is how the batch normalization works. So you take the batch samples, this is the batch sample dimension. You take the mean and standard deviation for each example for the same feature, and then you normalize them. You add these things for scaling and shifting the values. You will get the final features here. This is how it works. So by adding the batch normalization, they have actually improved the MAP by 2%. Also, as batch normalization is already having the regularization effect, they have removed the dropout layers from the YOLO-V1. So these are the modifications, whatever we are discussing are the modifications they have made on the YOLO version 1 architecture to make it more accurate. And the next one is high resolution classifier. So basically in YOLO version 1, what they have done, whatever the backbone they are having, they have trained it on the classification model, ImageNet classification, which is at 224 by 224. And then they have directly trained on Pascal VOC dataset at 448 by 448. This makes it difficult for the network to adapt to the increased resolution. You have doubled the resolution and you are trying to learn on a different kind of dataset altogether. So the network feels a bit difficult to adapt to the increased resolution and learn for the detection tasks. Now in YOLO version 2, what they have done is, after they have trained on ImageNet dataset at 224 by 224, they have fine-tuned the model on the same ImageNet dataset for another 10 epochs with the increased resolution. This is the resolution which we are going to use in the object detector. So they have used this same resolution for fine-tuning for another 10 epochs. This is still happening on the classification. And after that, at the final stage, they are actually using 448 by 448 for object detection. This should make it clear. First, they have trained on ImageNet 224 resolution, then fine-tuning on the ImageNet only with higher resolution. Now at this particular stage, whatever the weights learned here, they will again adapt to this higher resolution. And then finally train it on Pascal VOC for detection task at the same resolution. As it has already seen that resolution in ImageNet, this will be a bit easier for it to adjust. Another modification is, in YOLO-V1, we are starting with 448 by 448 and finally we are getting 7 by 7. You remove these fully connected layers, then you will get 7 by 7 1024. This is my feature vector as the output I am getting. So 448 by 7 by 7. So this is actually 64 times reduction. Now 7 by 7 is actually very coarse feature map to learn for the object detections, because we need the localization information. More context information will be there for 7 by 7, but you will lose some spatial or local information which is required for object detection. So that's why the model is not able to recognize the objects very well. Even the localization is not very well. Now we have to increase this feature map from 7 by 7 to some other higher dimension. How do we do this? If you observe here, there are some max pool layers, right? So what if I remove the last max pool layer? If I remove this particular max pool layer, then whatever 14 by 14 it is supposed to happen, it will still stay at the original 28 by 28 here. And then after that, at this particular stage, it will reduce to 14 by 14 and it stays the same 14 by 14. So here it is 7 by 7, whereas here it is 14 by 14 resolution. So this gives feature map with better resolutions. This will also improve the object localization. Now this 7 by 7 is actually indicating in YOLO-V7, 7 by 7 is actually indicating dividing your image into 7 by 7 grid cells. In the same way, 14 by 14 actually indicates dividing your image into 14 by 14 grid cells. So here it is 7 and here there are 14 grid cells. Now there is one issue with the 14 grid cells. See, because what happens is, if you have even number of grid cells, then there is no single center location. This is the center location I am getting. There is no single cell. Consider that center location. What happens if I have very big object like this? Then there are more chances that its particular center will come to the actual image center. Now there is no particular grid cell to assign to this, right? So if my object center is this, which grid cell it should look for? This one, which one it should look for? So that's why we always go for the odd number of grid cells or odd number of filters. Even the convolution filters or kernels, we use odd numbers because we need one centralized location. From 14 by 14 here, they have reduced to 13 by 13. If you see now, this has a central grid location, one grid location. So now finally in YOLO-V1 we are using 7 by 7 and this has been increased to 13 by 13 in YOLO-V2, which is much finer resolution. And they have made another modification which is called pass-through layer. If you see the convolution layers, they gradually reduce the feature maps layer by layer. And we need higher resolution feature maps for better localization because they have ingrained spatial features. So how can we use the feature maps from the previous layers to help in the final predictions? By using the parallel branch like this. A feature map of higher resolution, this is 26 by 26 and this is 13 by 13. So 26 by 26 is the higher resolution feature map. A parallel branch is taken here. This is actually 26 by 26 by 512. This is reshaped into 13 by 13 by 2048. So then this 13 by 13 by 2048 is concatenated with this 13 by 13 by 1024 coming here. Finally, these 2048 and 1024 became 3072. So this is how the pass-through layer work. But how can I actually reshape this one to this? So you have the equal number of feature cells, so you just need to reshuffle. So this is how you can do. So if you have like 26 by 26 here, now you can actually divide them into 4 grids. These are your 4 grids here. And then you just concatenate all of them. So each one has C number of channels and finally you will get 4 times C. So we have 512 channels and 4 times of this will give me 2048 channels. And this one I am concatenating here with the lower resolution tensor, which I will get the final total number of channels here, which is 3072. And adding this pass-through layer has improved the MAP by 1%. If you see, this is my final model after the pass-through layer. So this is my YOLO-V2 network. Now this 26 by 26 actually I have passed through here and I am reshaping as 13 by 13 by 2048 and here I am already having 1024. So finally I will get 3072 here. After this 3072 I am doing some other convolution layers to get these values. So that we will see later. But this is how the pass-through layer works. Now let's look at some of the issues with the bounding box predictions in YOLO-V1. We will solve them one by one. The first problem is YOLO-V1 can predict only 2 boxes per grid cell. It has 7 by 7 grid cells and each grid has 2 boxes, so total 98 boxes. 98 boxes are the maximum you can get from YOLO-V1. And there is one more problem, only one particular class probability you will get, so obviously at the end you are getting only 49, but at least the total number of boxes are only 98 here, which is very much lesser than all the other object detectors. SSD has in 20 case, so which is one of the reason YOLO-V1 has very low recall rate. That means it is missing detections. If you have more boxes, then you have more predictions and it is able to adjust one or the other way, different shapes, right? If you already have very less boxes in the beginning, then you have the chances of missing the objects. Now by making this grid cell from 7 to 13 by 13, we are able to increase to 338 at max, which is still much lesser than all the other object detectors here. So now what should we do? Should we make the grid cell to 50 by 50 from 13 by 13? How many we will get if you make 50 by 50? If I make 50 by 50 and each grid cell has 2, so I will get only 5000 boxes. Okay, 5000 is at least equal to or nearby fast RCNN, right? But if I want to predict these 5000 boxes, so here how much I should get? So here 30 values per each grid cell and 7 by 7. Instead of 7 by 7, I will get 50 by 50. 50 by 50 into 30. How much it is? It is 75k. So these many parameters I need at the output prediction. Now for that, how many parameters I need in these FC layers? How much computations I will be doing? So in only the FC layers itself, I will be doing millions of parameters, right? I will be having millions of parameters. This is not feasible. But then how these guys are able to get these many boxes? They are actually using convolution layers for the predictions. We are using fully connected layers for the predictions in YOLO. But in SSD or faster RCNN, the actual box predictions are happening in the convolution layers, not on the fully connected layers. So the problem is with the fully connected layers. So fully connected layers is limiting us with the number of parameters to predict. So the reasonable option is to go fully convolutional. So even with the YOLO also, we should go for fully convolutional layers. That's what they have done with YOLO-V2. So whatever the last 2 fully connected layers are there in V1, those are getting removed. And then they are replaced with a couple of convolution layers. Now as the convolution layers parameters are negligible compared to FC layers because you have the same kernel size which is shared across the whole image, right? So the parameters are very much less. So now with the fully convolution layer, we can increase the number of boxes per grid cell or we can increase the number of grid cells also, right? So these number of predictions, whatever we are getting, 7 by 7 by 30 in YOLO-V1. These predictions we can keep how many ever we want. But still we have one other problem. A particular grid cell we are only getting one particular class. So if I have 10 boxes in a grid cell or 50 boxes in a grid cell, I will still get only one class, right? So finally, my number of objects will be only one. If I don't have class predictions, I can't use that box anyway, right? So I will only pick up one of the box which is having the highest confidence score. So this is another big problem, right? So this is actually limiting our number of objects, right? In YOLO-V1 it is 49. We can only detect maximum 49 objects. If you increase to 13 by 13 also, maximum 169 boxes you can detect, right? Maximum 169 objects. If it is a very crowded scenario, like a crowd gathering or these kind of things, you have chances that you will get more boxes, more number of objects there. Now how should we go for this one? How can we solve this one? So instead of predicting only one class per grid cell, we should predict the class for every box, right? That is the solution. We have to predict the class for each box. Then every box has its own class, so you need not to discard the boxes. This will increase the number of objects that can be detected. If I have 100 boxes, 100 classes I will have. So I can easily detect more number of objects. Now let us look at the reasons for poor localization. In V1, we saw that the localization is happening with respect to the grid cell top left corner. Width and height are actually happening with respect to the total image width and image height. This is what it is happening in V1. But if you see, the objects can be of different shapes, right? If you see the person, this aspect ratio and shape is different. Some objects are small, some objects are very big. If you see this bus, this is almost occupying the whole image. Now, predicting these kind of bigger objects from a single grid cell here is very difficult, no? Because you don't know what is the shape of this object, how much range you have to look for in your predictions. So it can be difficult for the network to predict directly these boxes without any prior information. So what should we do? In this case, if the bounding box regression is very difficult, what should we do? We should go for anchor boxes. That means we should at least get some prior boxes which will give some information to the network about how the object looks like. Those are called anchor boxes. So what are anchor boxes? Anchor boxes are predefined set of shapes. So these are already defined set. Like I know that, okay, this is how the person box should look like. This is how the car looks like. Or this is how the total building looks like this. So these are some of the aspect ratios and samples of already detected objects. Like if you take Pascal VOC or COCO datasets, we already know that this is how the person looks like, right? So this is a known information. Why don't we feed this to the network? That is what we are doing in the anchor boxes concept. So the bounding boxes now, instead of detecting with respect to the grid cell, we will actually predict with respect to these anchor boxes. So if I have a person here and if I start with this particular anchor box, I will easily fit this box to the person, right? So the network can easily learn how to fit this particular box to the person. That is actually easier. In FastRCNN, they have actually used 9 anchor boxes for each location. There are 3 different scales and 3 different aspect ratios. For person, let's say this is the box. Now for the same box, at bigger scale you will get this one, and much bigger scale you will get this one. Same way for car, let's say this is the box at small scale. The same shape, you will get bigger boxes and you will consider another much bigger box like this. So 3 scales and 3 aspect ratios, total 9 boxes. That is what FastRCNN is using. So YOLO also adopted this anchors concept. This results in slight MAP drop by 0.3%. It has reduced from 69.5 to 69.2. Even though MAP has reduced, they have observed that recall has improved. Recall means the chance of detecting the objects, right? That means it is not missing the objects anymore. So this also indicates that the model has more chance for improvement. How can I improve the MAP? Okay, recall has improved. That is very good. But how can I increase the MAP? It is reducing with the use of anchors. So instead of using the fixed boxes, why don't we choose the anchors based on the data set? We know that the existing anchors also has some kind of predefined boxes, like this looks like a person, like this. But what if we generate these anchors based on the data set we are training on? Let's say I am training on only the birds data set. So birds data set, I will never get this kind of box, right? Very less chances that I will get that kind of box. So if I choose the anchors based on the data set, that is well and good. How do we do that? By doing the clustering. So what we do is, you take your data set and perform clustering on all the ground truth boxes. If you have all these ground truth boxes, on all these ground truth boxes of your whole data set, you perform the clustering with different k values. Maybe you can start with the 3, 5, 9, like that. Because we don't know how many varieties of boxes are available. So you can try with different centers And what happens is, if the similar kind of aspect ratio, these boxes are there similarly, they will actually combine and give one centroid here like this. So finally you will get groups of objects, groups of boxes, which will have one particular centroid for each. So how many ever centroids you are having, that will be your number of anchors, and the average of individual centroids will be your anchor box. If you observe this, these are actual average shapes for Pascal VOC. For Pascal VOC, this kind of shapes are more, these kind of shapes are more, this is the average shape we got, and these are the particular locations. Like this is existing here at this location, this is existing here, this is existing here, like this. So we will get these kind of average shapes and locations. Now, if I want to train my model on Pascal VOC, I can directly take these boxes as the anchor boxes, because I know that these are the average, these are the most prominent shapes available in my dataset. They have done the experiments with different number of clusters, and finally they have selected 5 boxes as the optimal boxes. That means 5 anchor boxes. They are predefined anchor boxes which are used in FastRCNN. This is having average AOV of 60. Whereas if I do clustering on Pascal VOC with only 5 boxes, still I am getting more intersection with the ground truth boxes. That means this 5 is representation, whatever we got here, these particular 5 boxes representation is better than the 9 fixed anchors in FastRCNN. It has almost reduced the computation by half and keeping almost the same accuracy. Right? So this will solve the problem of poor localization to some extent. Now there is one more problem. In YOLO-V1, we did not use any kind of softmax or sigmoid activation functions because everything is a regression problem. So we are using only linear activation. In the intermediate layers, we use ReLU activation, leaky ReLU. So linear activation, it will not restrict the values. So the values can be ranging from -infinity to +infinity. Whereas in the targets, we have to predict everything with respect to the grid cell. This is the top left corner and this is my center of the object. I will have to calculate the offsets here with respect to the grid cell like this. So the values are normalized between 0 and 1. Your predictions are ranging from -infinity to +infinity and your targets are 0 to 1. So you will have very high loss actually, so which will cause unstable training. Now what should we do? We should actually restrict these things. Instead of predicting from -infinity to +infinity, we should predict in the restricted range. If my targets are 0 to 1, why not predict these things in the range of 0 to 1? So that is what we have to do, constrain the predictions. For doing that, first thing is we apply the sigmoid function, and the second one we use the exponential function. Sigmoid function, it will actually convert any values between 0 and 1. At the same time, exponential function, it will convert any value into only positive values, 0 to +infinity. So for the xy coordinates, which is the center of my object, for this particular thing, I will actually do sigmoid on top of the predictions. So this tx, ty, tw and th, these are my predictions. On top of the predictions, for x and y coordinates, I will apply the sigmoid. And then for width and height, I will apply exponential so that it will not have at least negative values. So by doing these operations, I am actually constraining my predictions. Now if I compare these values, which is the output of this, I will have the values between 0 and 1. My targets also having the range of 0 to 1. So I will get low loss values. And they have faced one more problem. Now they started adopting these anchors, right? So when we get these anchor boxes now, and let's say your object is in the shape of this one. Now for this center of my object, I have to predict with respect to the anchor top left corner, and width and height I have to predict with respect to the anchor width and height. That's what it is happening in FastRCNN. If you see, these are XA, YA, AA, HA. These are the anchor values. And this TX and TY are my network predictions. These are my actual box predictions. Now for getting the actual box value, I have to use the anchor predictions. So the offsets are calculated relative to the anchor boxes. So now because of this one, they started facing instability in the training, especially in the starting iterations. So what they have done is they reverted back to grid-based approach, especially for X and Y. So the center values X and Y, they reverted back to grid-based approach. So they are not doing any more on the anchors. This they are not doing. They are doing with respect to the grid values. So this is how they have modified. So if you observe this one, this is actually CX and CY. These are the grid position, whatever my grid is there, in which the object is available. This is my object grid cell. This particular grid cell, how far it is from the top left corner of the image. These are CX and CY. The dotted values are my anchor boxes, and this blue value is the actual prediction. Now from the network, I will get Tx, Ty, Tw, Th. These are the network predictions I am getting. Now this Tx and Ty, I know these are with respect to the grid cell. How can I make use of these 4 values now to get this blue box? This blue box is my target. How can I get this box from these offsets? Using these formulas. If you see, Tx and Ty are with respect to the grid cell, and with this we are actually adding this Cx and Cy, which are actually the offset, which will give me the final center value here. And then W and H, I am actually applying the exponential function. Here this is actually sigmoid function. Similarly here for width and height, I am applying the exponential function and then multiplying with the anchor width and height. Okay. So if you see what change we have made in faster RCNN, even this XY coordinate also getting predicted with respect to the anchor top left corner. Whereas now XY coordinate I am predicting only with respect to the grid cell. Whereas width and height I am predicting with respect to the anchor. Because anchor is actually shape. It doesn't matter where the center of the anchor locates, right? So we are only looking for the shape information from the anchor. So width and height I am predicting with respect to the anchor. So along with that, we will actually get one more prediction for each box, which is actually objectness score. This is almost same as YOLO-V1, which is your IOU between the ground truth. Okay, and class probabilities for each box. So for every box, we are getting the class probabilities here. This depends on the number of categories in your dataset. So to get the overall picture, we are actually considering 5 anchor boxes. Okay, for every grid cell, we are considering 5 anchor boxes. And for every box, we are predicting 5 values here, which are X, Y, W, H, and then objectness score. And 20 class predictions, because it is a Pascal VOC dataset. Now total 25 here, right? So 25 values I am predicting for each box. Now for each grid cell I have 5 boxes. So which will give me 125 parameters for each grid cell. So for if I'm grid cell is this one, for this particular grid cell I will get 125. Like this in YOLO-V2 we have 13 by 13 grid cells. So the total number of parameters will be 13 by 13 by 125. This should be the output I will be getting from the network. So this will be network output. This is how the output predictions looks like. If you have k boxes, let's say we have 5 boxes here, k equal to 5. For every box you have the coordinates, you have the confidence score, you have the class probabilities. Okay, in YOLO-V1 you have only coordinates and confidence for 2 boxes and class probabilities are common. Whereas here for every box you have the class probabilities in YOLO-V2. This is the difference. And this is the main difference between the output predictions. If you see YOLO-V1, we need only 7 by 7 grid cells by 30 predictions. Whereas in V2, we need 13 by 13 grid cells and each grid cell we need 125 parameters. So you can see the number of parameters increase. So with all the modifications we have done so far, like adapting the anchor boxes or calculating the things with respect to the anchor box and then changing to fully convolutional, all those things actually improved my MAP by 5%. Now we have seen the output predictions. Let us look at the targets. So the target calculations are almost same as YOLO-V1. Only difference is in YOLO-V1 we calculate the target per grid cell. Here we calculate the targets for each box. A grid cell has many boxes here. So still we consider the anchor box with respect to the IOU with the ground truth, and grid cell we will consider where the object center falls. That particular thing is responsible for that prediction. The same way we consider as in case of YOLO-V1. Now our targets needs to be generated for every grid cell and for each grid cell for every anchor box. Okay. So as you can see, X and Y are still relative to the grid cell only. Even though anchors are introduced because of instability in the training, they went with grid cell approach for X and Y. Whereas width and height, which are actually giving shape of the object, those should be relative to anchor boxes. In V1, these width and height are actually relative to the whole image. Now it is relative to only anchor box. And the targets for the objectness score is same. 1 for the cells with objects and 0 for cells without objects. If there is no object, then it is 0. If there is an object, then it is 1. And the class probabilities target is always one hot encoding vector. If you have 20 classes, you create a vector with 20 values and make one as the particular class, others are zeros, like this. So that one hot encoding vector, it's the same as YOLO-V1. This is all about the target calculations for YOLO-V2. It's almost same as YOLO-V1. There is not much change. Now let us look at the loss function. This looks similar to YOLO-V1. The losses we are still using squared error losses everywhere, but there are some minor modifications. Like this is one extra term here. and this is one extra summation here like this. So we will see one by one. Now first we will see this particular block. If you see this particular block, so this W and H are actually S by S. So for every grid cell here, every grid cell has 5 anchors, A equal to 5. So for every anchor also we are calculating the loss. Earlier in YOLO-V1, we are only calculating the loss with respect to grid cells. Now we have to calculate the loss with every anchor box. Okay, that is what this particular third summation indicates. Then the first term is loss for no object cells. That means if a grid cell doesn't have any object, then the loss is this one. If it doesn't have any object, then obviously it will only have objectness score. It will not have class probabilities or it will not have box predictions. And for objectness score, if there is no object, then the target will be 0, right? 0 minus whatever my predictions. So the 0 doesn't matter. So this is actually negative sign coming here. So this is the prediction here. And this lambda no object is actually kind of a weighting factor, which we are using the same way in YOLO-V1. And then this is one additional new term we got in YOLO-V2. This is with respect to the anchor priors. So we are actually calculating the loss for the alignment of anchor boxes with respect to the predictions. So here prior means anchor box. So we are calculating the square root difference between anchor box and the box prediction from the network. But this we are not doing for all the iterations. We are only doing for starting 12,000 iterations. After this loss will not be getting calculated. And then we have the bounding box prediction. This truth is your ground truth, or maybe you can say targets. So this is just the square root difference between the ground truth labels or targets and the network predictions for X, Y, W and H. This is for the objectness score. So objectness score generally we calculate with the IOU of ground truth. So it will be 1 for the cells with objects, otherwise 0. So for 1, it will actually get the objectness score of the predictions. So it is just the square root difference between both. So here it is 1 minus some value like 0.8 or something. So like this you calculate. And these lambda values are actually weightage values. How much weightage you want to give for this particular loss value, like this. And the same way for class probabilities, this particular ground truth, if you have 0, 1, 0, 0, 0, like this. And this particular thing you have 0.1, 0.8, 0.05, 0.005 and 0.005. Now these individual terms I am calculating the difference and then summation of all the individual differences. So this is how you calculate the square root difference between class probabilities and the labels. This is the total loss function. Everything is the square root term here. All these are square root terms. Okay. Only additional term is this one. This is actually for anchor box alignment. This is the loss between the prior, that is anchor box, and the box predictions. And this is for the no object cells and this is for the object cells. Now that we have finished the loss function, we will see how the training happens. In YOLO-V2 they have started multi-scale training because we saw that YOLO-V2 is actually fully convolutional network. We removed the fully connected layer. So without that fully connected layer, we can actually give any number of input resolutions. Okay, we can change the input resolutions. Network can take any input image resolution, but we need to make sure that the resolution should be a multiple of 32 because network is actually degrading from 416 to 13 by 13, which is 32 times. So it is reducing the feature map by 32 times. So the resolution also should be multiple of 32. So they have experimented with multiple different resolutions starting with 288 by 288 till 608 by 608. For every 10 batches, one of this value is randomly picked. And this random pick, maybe it can be 320 for the first 10 batches. Later it can pick 608 for the next 10 batches, like this. So, and then it will train for 10 batches, one resolution, like that. The training happens. This actually acts as the data augmentation because you are actually sending images at different resolutions for different training iterations. So this kind of data augmentation actually helps in predicting the objects at different scales. If you have smaller objects, it might get predicted if you have larger resolutions. And one more thing is, for smaller resolutions, you have actually very good speed. Your FPS is very high, but you have less accuracy. Still, you have very good speed. So let's say this 288 by 288, I am getting 90 FPS. But 544 I am getting only 40 FPS and the difference is 10 MEP loss. So if I am fine with this 10 MEP loss, I can get 90 FPS speed. So we can choose the resolution depending on our requirement. There is always trade-off between the accuracy and the speed. If the speed is more, then the accuracy will be less. Now with all the improvements we have made so far, this is the improvement in MAP we have got. If you observe the initial YOLO-V1, it is 63.4 and finally we got 78.6. You can see 15% MAP jump with all these modifications, starting with batch normalization, high resolution fine tuning on the classifier, fully convolutional anchor boxes and dimension priors, which are actually anchor boxes but with k-means clustering, and location prediction, that modification of XY with respect to the grid cell, and then pass-through layer, multi-scale training, high resolution detector, changing the different resolutions, right? If I use high resolution, then I am getting 78.6. So with all these modifications one by one, you can see how much each one has impacted. Batch resolution has increased 2%. And adding high resolution classifier has improved by 6% compared to the original. So you can see all these differences. And this is the speed versus MAP comparison of YOLO-V2 with SSD, different versions of SSD and faster RCNN. So you can see that if it is increasing like this, that means MAP is higher and this side it is much faster. So if you see this particular one, the highest one, which is having 78.6 MAP here, that is still faster than SSD and faster RCNN. Okay, only 300 version, SSD 300 is a bit faster than that. And as the resolution got reduced, as we decrease the resolution, we are actually increasing the speed. We are getting high speeds, but the MAP is getting decreased here. So these are the results for Pascal VOC. Now we will see the results for COCO. In COCO dataset, YOLO is actually slightly behind the faster RCNN as well as the SSD. And that too, for SSD, the higher model, 512 resolution, it is a bit more compared to YOLO-V2. And faster RCNN, it is 45. YOLO version 2, we are getting 44. This is on COCO dataset. But still, if you consider the FPS, we are getting very high FPS in YOLO. So still it has an edge of speed. So 1 MAP, 2 MAP difference, if you are okay with that, you are getting 3 times, 4 times speed compared to faster RCNN. So far, whatever the modifications we have seen, those are made on the original YOLO version 1 architecture. Now, finally, they have actually came up with the new architecture because they wanted the model to become faster. So they came with the new architecture, which is called darknet 19. It has 19 convolution layers, which is the reason darknet 19. If you see the darknet 19, and this is the original YOLO-V1 architecture, the number of parameters, it has 8.5 billion and darknet 19 has 5.5 billion. And you can see the top 1 and top 5. This is actually ImageNet classification scores. You can see it is still better than YOLO-V1 and it is faster. This is 180 FPS and it is 200 FPS. If you compare with VGG or ResNet, it is much better, definitely, because these are heavy models. But if you compare with the YOLO version 1, the original model used in V1 also, it is lightweight and it is much more accurate. So this is the new model they have actually used as a backbone for YOLO object detection. So this is the backbone for the classification. So these are actually 19 convolution layers. In between, some max pool layers are there. But then finally you got one softmax with for the 1000 classes. This is for classification. Now for the object detection, they have made few modifications. First thing is the last fully connected layers and the last convolution layer they have removed. And they replaced with 3 convolution layers after that. 3 convolution layers. These are 3 by 3 convolutions. And then there is one pass-through layer. We have already seen this pass-through layer, right? And then after the concatenation, actually we will get 3072 feature map. And then by using another convolution, we are getting the feature map of 1024. And then we are getting another convolution, we are getting 125. It is actually 13 by 125. This is the final feature map we are getting here at the end. So this is all about YOLO-V2. Now there is one more thing pending from this paper, which is actually YOLO9000. This is a completely different approach they have followed for detecting these objects. So we will look into this in the next video. Thank you so much.